Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 26, and this problem asks us to draw the product of each reaction. So what we have in each of these is an electron-poor benzene ring, and what we have is this electron-poor benzene ring is reacting with a very strong nucleophile, being a full NH2 minus with ammonia. So we can obviously assume that this is going to be a nucleophilic aromatic substitution. Why? Because now in this case, our benzene ring is now going to be the electrophile while we have a nucleophile as one of the reagents. And this is opposing the electrophilic aromatic substitution in which the benzene ring was a nucleophile and our reagent was the electrophile. So this type of nucleophilic aromatic substitution is different than the problem we did before in problem 24, such that instead of having addition and then elimination of your leaving group, you're now first eliminating your leaving group and then you're adding your nucleophile. So this is what we call elimination addition reaction. And this is opposite to the question 24, which was addition elimination. Now we have elimination addition. So we're first eliminating the leaving group in this problem, and then we're adding the leaving group. So if we work through the mechanisms here, is that we have an electron withdrawing chlorine halide here, and we're having a strong nucleophile. So we can say that because this is not only just a strong nucleophile, it's also a very strong base, it's going to rip off this acidic proton, making a triple bond here. And when you make a bond, you break a bond, so your leaving group, being the halide, chlorine, is going to leave. And now what you have here is now you have this triple bond with ammonia being formed, and then you have the original ammonia, which is the reagent. But now this ammonia, with its lone pair electrons, can attack this benzene ring, making a bond. And when you make a bond, you need to break a bond. So one of these triple bonds is going to break, go through this carbon nucleus, and it's going to pick up this proton that was ripped off, making a bond. You make a bond, you break a bond, and now you reformed your, you could say, basic catalyst. So now what you have is that we first eliminated your leaving group, and then we added the nucleophile, so we have an elimination addition reaction. And you're reforming your basic catalyst, was what you could call it. And then that basic catalyst can also, because now nitrogen would have a positive charge, so that basic catalyst can actually just deprotonate this nitrogen. So you would just get an NH2. Plus you reform your ammonia. So now in B, you have something similar, but now this time we have sodium hydroxide, which you know is a very strong base in water, and heat. This triangle just means heat. So once again, we have this acidic proton that can be ripped off by this hydroxide, making a bond. You make a bond, you break a bond, so you form this triple bond here, making a new bond. When you make a bond, you break a bond, so your chlorine will fall off. And what you see here is now we're left with this triple bond, methoxy substituent, and we form water. And now we have more molecules of this OH minus in solution. So now we have two options here, because this is not a symmetric molecule as of yet, or after this reaction. So now we have this oxygen, negatively charged hydroxide, that can attack on this carbon, the ortho carbon to this methoxy group, making a bond. You make a bond, you break a bond. So one of these triple bonds will break to pick up the proton from water to reform your base. Sorry, this should have been on this carbon here. So let's fully redo this. The triple bond, I drew it on the wrong carbon. So this triple bond, now that I'm looking at it, should be on this carbon here, actually. So it makes sense because we had a para-substituted benzene with this leaving group, so now the triple bond is going to be here. So now, moving on from this position, it makes sense for another reason, which I'll tell you guys in a second, but now we're attacking now the meta position, making a bond. You make a bond, you break a bond, so then the para position will pick up this proton, and this forms one of your products. But now at the same time, with equal chance, the hydroxide could have attacked the para position, making a bond. You make a bond, you break a bond, so then the proton would have been added on the meta position. So now what you have is two products, one being a para substituted, one being a meta substituted through hydroxide through nucleophilic aromatic substitution. And this is what I wanted to get to, is that when you have already substituents on your benzene ring, your nucleophile will add in one of two positions, one being the meta position, one being the para position. That's because your alkyne bond, that triple bond, has two sides. The left side, in this case, is the meta position, which is the blue product, and the right side is the para position, which is the red product. Now, what about for this example here? So this example, once again, we have a strong nucleophile, NH2. We have this chlorine here. We have this acidic proton here. So we know that this NH2 is going to pick up that proton, making an alkyne bond. When you make a bond, you break a bond, so the chlorine will fall off. So now in this situation, once again, we now formed ammonia. But now we will use the NH2 minus as our nucleophile. Once again, we can attack the meta position here, making a bond. And when you make a bond, you break a bond, and that's going to go through the ortho position to pick up that hydrogen to reform your base. So what you have here now is this meta-substituted addition product through nucleophilic aromatic substitution. And now we might be wondering, well, what about the other position? Well, if we attack on this side, this carbon here, well, this carbon is adjacent to this ethyl substituent. So this carbon is actually more sterically hindered than the carbon over here, which we have attacked through the meta position. So it's less likely that we'll have nucleophilic attack on this carbon than on the bottom carbon. So the major product is going to be this meta substituted product, and there's actually going to be a minor ortho product that's formed, if any at all, because of that steric proximity to this bulky ethyl group.